Hey Chem Kids, Campbell here. In our first video in Unit 3, we're going to continue talking about the development of atomic theory. But to do that, we're going to go back in time. So even way back when, people always knew that when you burned different things, you got different colors. In fact, when we do the flame test lab, we'll see that copper, when we burn it, is actually green. Sodium is kind of a boring yellow. But our eyes see one color. But actually, if we took a prism and we separated out the colors, we would actually see that each element has a specific color profile, which is totally cool. So before we go into what that means about atomic theory, let's talk about what light is. So light is an electromagnetic radiation. It's actually the oscillation of electric and magnetic fields. And it has these wave properties, but it is just a form of energy. Now, you need to know what these wave properties are. One is wavelength. Wavelength is a distance. It's just a measurement. It's the distance between like two light peaks or two troughs or two any identical points, but it's just a distance. That's what wavelength is. Frequency is actually related to time. It's about how many peaks pass a point in a given amount of time. And in fact, the frequency has a unique unit. It's called the hertz. Another property of light is speed. What's really cool about light is all light travels at the same speed. And in fact, in a vacuum, that's 3 × 10⁸ meters per second, which is super fast. In fact, that's why you see lightning before you hear thunder, because sound travels much, much slower than light does. Now, how are these things related to each other? So wavelength and frequency are actually inverses. They're inversely proportional to each other. So that means if I have a short wavelength, I have a high frequency. Or if I have a long wavelength, I have a short frequency. But like I said, light is also energy. It's a transmission of energy. And energy is directly related to frequency. But that means, therefore, it's inversely proportional to wavelength. So if we take a look at the electromagnetic spectrum, you can see down here where I have very high frequencies, right? Those are big numbers. I have very short wavelengths. And you can see that these guys, the gamma rays, the X-rays, the UV rays, right? All those things do damage to your skin. It's because they have very high energy, right? High frequency, high energy, short wavelength. Then here we have the visible spectrum, which is kind of like in the middle ground there. And then when we get down here where we get to these shorter frequencies, much longer wavelengths, we get down into, oh, there's your cell phone. There's radio waves, microwaves. So these all have low energy because they have a short frequency and a long wavelength. So just if we look within visible light, the stuff that our eyes actually can detect, right? Here's the visible light spectrum, Roy G. Biv, right? Here's the Biv part. Biv actually has the shorter wavelengths and the higher frequencies, where red is the longer wavelengths and the low frequencies. And so that means that our purple light up here, the violet stuff, has a much higher energy than the red light down here. Now, light behaves like a wave, but it also has particle properties. What? How can light be a wave and a particle? Well, the photoelectric effect was actually an experiment that Einstein used to show that light had particle properties. In fact, what the photoelectric effect is that if you take a light that has enough energy, right, a high enough frequency, a short enough wavelength, on metal, you can actually eject electrons. You can strip them away from their atom. So in fact, if we take a look here at this metal, this is potassium metal down here. If we shine red light, remember red light had less energy on it, we don't get any electrons. Nothing happens. But if we start to dial up that frequency and go to, say, a green light actually starts to eject electrons. And every light that has a shorter wavelength or higher frequency than green light will do that. And what's interesting is that this also proves that light has energy and that frequency is related to energy, because the more we dial up that frequency, the higher the frequency gets, the more energy those electrons have when they come out. Totally cool. So the photoelectric effect demonstrates the particle nature of light. What? Now, like I said, Einstein was the one who explained the particle nature of light because of the photoelectric effect. So what he did is he theorized that light are just packets or particles of specific amounts of energy. And so these packets of energy were later called by Gilbert Lewis photons. But so that's what a photon is when you hear about photon torpedoes. Photons are actually just specific amounts of energy. That's it. That's what light is. Now what? But wait, I said that light behaves like a wave too. So it's a wave and a particle? How can that be? Well, this debate raged on for a long time because you run some experiments, light's a wave. You run some experiments, light's a particle. And so it took a long time before we could wrap our head around the fact that light could be both, that light has a dual nature. Okay, so what does this have to do with these unique spectrums for each atom? So here is actually specific one. So you can see down here, here's sodium. Sodium, when it burns, it's yellow, and this is why, because it's pretty much all yellow. But if you take a look at calcium, calcium has some red and oranges, it has yellow, it has some blue and some violet. So different elements have a unique fingerprint of light, of photons. Like what? So Max Planck was like, okay, if these have this specific amount, if only specific wavelengths of light are given off by certain elements when we burn them or put energy into them, that means that elements must be restricted to certain packets of energy, certain pieces. And he called those pieces quantum. So quantum, they're just like a specific amount of energy. It's a fancy term, but that's really all that means. It's just a specific amount of energy, and that each element has its own energy profile. He wasn't all that comfortable with it, but because, how do you explain this? Like, you have a positive nucleus with these electrons moving around them, and they have specific amounts of energy. Well, that's where Niels Bohr came in. Niels Bohr proposed this planetary model of the atom that, like here's the sun and then everything else is orbiting around it like planets. So in the middle is their nucleus, right? Rutherford came up with that. And around the nucleus, there are these specific energy levels. They have a certain amount of energy, and he labeled them 1, 2, 3. So the lowest level here is n equals 1, and it goes out and out and out, but they're always specific amounts. And so this lowest level actually has a name. It's called the ground state. So n equals 1 is the ground state. It's like what I like to call the happy place for everything in life, right? To be at the lowest level possible, our lowest energy level possible. But eventually we shine light on an element, we put it in a flame, we zap it with some electricity, and electron will absorb energy from that, and it'll go to what's called an excited state. So it'll go from its ground state here, and it'll go up to a higher level. That's actually called an excited state. It doesn't stay there forever, though, because eventually it's going to fall. And when it does, that's when we get to see those color profiles. That's when we see the different colors coming out. So let's just go through this one more time. That every element has a specific energy level that are called quantum. And that you can kind of think of them like stair steps. And as we go out from the nucleus, as our shell number, our n value, 1, 2, 3, 4 increases, the energy increases. And so if light is absorbed, if energy is absorbed, it'll make an electron jump up to a higher level. That's called an excited state. But eventually, you can't stay at a high energy state forever, right? If you were a runner, you can't run forever. Eventually, you have to stop. So when that happens, the energy has to be re-released. And when it gets released, it actually is emitted as a photon. So that color that we see is due to this energy being released as electrons fall back into their ground state. And Bohr's prediction actually worked perfect for hydrogen. In fact, in class, we're going to take a look at the hydrogen spectrum. We'll be using some spectroscopes to actually break out the different colors so we can all see them. But really what hydrogen is, and what Bohr proposed, is that these different colors, these different wavelengths, these different photons that we're seeing are actual falls of the electron from an excited state to a lower state. So in fact, when we see red, it's a fall from level 3 to level 2. And when we see that green color, it's a fall from level 4 to level 2. And so these transitions, these movements of the electron from an excited state down to a lower state are releasing energy, and that energy we see as light, which is really cool. Now, you may wonder why, I said everything ends up down in the ground state in its lowest level, why these aren't the ground state ones. Well, actually, those exist. It's just that our eyes can only see the visible spectrum, which is a specific range of frequencies. So the other ones we just can't see. They're there, but we can't see them. And speaking of seeing them, I'll see you in class.